Hey guys, welcome again to my YouTube channel. Today we'll be solving the word search problem. Let me just summarize this problem in my whiteboard. So we are given a problem where a board is given to us. It's a collection of characters, and then we are given a list of words. And our responsibility is that we search for these particular words in our array. Now we know from graph-based traversals, if we run a BFS or a DFS, we can ideally come up with a solution. But in this problem, the time complexity demanded is much less, so we'll have to some way come up with the optimization, and that's where you're trying to solve or come up with a better optimization. So our objective is, when we look at the problem in our traditional DFS sense, we just go to one of the element and look at its right neighbor, look at its down neighbor. We look at all possible directions, and we just explore all the directions, and we see if that finally equals the word that we are trying to search. Instead of that, if we can, eliminate some of the options, some of the directions. For example, let's say we are at C, and on my left I see a B. Now if I look at my word list, and if I'm really smart, I can say that after following a character C, there is no element in my word list that follows with a character B. So we never have a B which follows the character C. So here, when it says I see a B on my left side, we can simply eliminate that. We can say, oh, I don't see such an element in my word list, so going in that direction will never help. So by this, we can save a lot of exploration steps that we do in a classic DFS. But from an implementation point of view, can we think of a data structure that can help us do that? There can be many, but in this problem we are going to exploit a trie data structure. Now trie, we know that it has a root node followed by its children's. So let's say we are inserting the first character, which is a car. It will say C followed by sec A followed by R in the third level. And now if I want to insert cat, I just go and see from my root element, do I have a child called C? I already have it, so I can reuse it. Followed by A, I already have it, so I can reuse it. Followed by T, I don't have it, so I'm going to insert a new one. And then followed by Agra, I'll have a A. There is no G in the second level, so G and R and A. All right. Now from this trie data structure, we do something called, every traversal that we do, we make sure that we have another iterator which is pointing at trie. So let me just pull up another pen and put this iterator here, and let's just try to do a exploratory step in our using a DFS in our board or grid. So at the first element, I'll go to my C element, and this is the first optimization that I can come up with. I'll just ask this question: is there any element in my word list that starts with C? If it starts with C, then it makes sense to search for a word. It makes sense to start the exploration from this particular element. Otherwise, if there are no element that start with C, let's say E, if there is no element, we are doing all these steps in the hope that we'll find a word like this, but we'll never find. So we can do that optimization using a trie very easily by just asking this question from the pointer: does any of its child have a character C? That's the question we ask. Now it does have, so it makes sense to do the traversal process. So I'll go to my left direction. In my left direction, it will be prune because it's out of bounds. I'll go on my top. That is also prune because it's out of bounds. if I go to the right of the character C, I see a A. Now at this point in time, when I go to the next traversal process, I'll update my iterator to this point. Since I've selected a C element, this C element, since I selected it, I'll now update the iterator. Now, it's the same question. Do I see a child of C with a character A? Now it does. So we go here, we say, okay, it's a A, so it makes sense to carry on this part and do our exploration. But if it was some other element, it wouldn't have made sense to go in that direction. So now that we see a and we see in our try that in the current iterator's children has an A, and so we can go down this path, hoping that we'll find an element in our list. So let's just go complete this one. So on our bottom we see another A, and again, as we see in our priority queue, it does make sense to go and do a traversal in this path. Let's just go and do one more step in this process, and maybe we can collect some hints, and which will help us a lot in the implementation steps. So at this A, now I'm in this particular location. If I go on my left, I'll have to mark it as visited. I don't have to visit my those particular elements which I've already visited. So on the top it gets pruned. So on the left it's already visited. On the top it's out of bounds. On my right I see a T. So when I pass this function, when I do this traversal, I have to make sure that I update my iterator to the next point in the try. Now the same question. Do we see an element T in our try as a children or as a child of A? So in the child of A, we have two candidates, which is R and T, and we are hitting one of the candidate T. So that means we can still go on in this direction to search for words. Now during the insertion of try, it's important to note that we'll do one small changes, and it's important because at the end of this place we'll also say, in order to mark the end of a try, we can also mark it as end and make sure you collect all the elements in the path. Otherwise, from an implementation standpoint, you can insert the entire word in this place. You can just say, I'll make this slightly bigger. You can just say at this point it is car. You can say at this point it is cat, and then the last element is going to be Agra as a word. So when you hit the last element, you can ask this question: if the word attribute in a try, let's just say try has two attributes, one is the children's and the other is the word attribute. The word attribute for all these elements will be none, but for the last node we'll have it as the word in itself. So we can ask this question: if the iterated dot word is not none, then that shows that it is the terminal node in the given try. So if I hit this point, I'll make a check. I'll ask this question if it is the terminal node. If it's a terminal node, I can stop here and make sure I collect it in my result array. Now by doing so, we can make sure that we collect, or we go down in the path which only adds, which has a prospective word which is given in our word list. So just to reiterate, just to put it all these things together, we are trying to optimize by looking at our try and making sure that we only select those paths in which we have a potential prospective element of a word array, so that we avoid the other path traversals, and that way we optimize the solution. Now let's just go and write the code for it. Let's quickly go to our LeetCode and let's work on the implementation. So in order to implement, what do I do? First, since I'm going to use a try node, I need a try data structure. So I'll create a new class, and the class name would be a try node. Okay, the syntax does not require the braces, so I'll remove that. And now it will have a constructor which will which has the job of initializing two important attributes. The first attribute will be the children. The second attribute will be the word. Now, by choosing it, the word as an attribute, it really helps us in our following steps. So that's why we do this change from the classical way of just having a flag called is this the end of the try. All right. Now we have another function. I'm going to call it the add to the try function, just an add, which will take in a word and add it to my try node. So initially we have an iterator kind of a node which will take the value of the root. In this case it's a self. Now for every character in my word, I just need to insert it. So how do I insert it? I can just say if the character is not in the node.children, then I have to create a new try node at that particular point. So I'll go to children of character, and that I'll initiate to a new try node. Now it's time to go to the next node pointer. So I'll say node.children of that particular character that we just initialized. I'll go to that object now. So node will represent that object. So character. This would make sure that that node promotes or progresses into the next newly initialized try node. All right. If it comes out of the for loop, I'll make sure that I set the word attribute for all the nodes. For the other nodes, it will be none, but only in the last word after the completion of for loop, I'll put in my input word that is given as the value for the word attribute. Now let's just go to our main solution and add all the words that we are given into our try data structure. So in order to do that, I have to first initialize a try node. Try node followed by, now here's the logic. So for every word I see in my words array, I just have to insert it. So in this case, root dot add, I have this method inside, add these words to my try data structure. Okay, now I'll initialize this result value. This will help us to store the result as and when we find it. Now I'll just initialize a internal DFS function. It's internal because it helps us share a lot of variables while organizing it into a separate function or a method. So now the first thing that we check in DFS is if it is out of bounds. So R and C, which are the parameters, we'll check if that is less than 0, or if C is less than 0, or if R exceeds or equals to the len of the board in itself, or C exceeds or equals the len of the board of the 0th element. In this case, in all of these cases, we have to just return false, or say we don't have to progress into the next path, otherwise we'll get an error. We'll add another condition, which is to say if the board of element is marked as already visited, which we'll mark by a character hash. So we'll say that in right here, we'll say board of R comma C. If you see that value to be a hash, even then ignore it. So just return and we'll not go and explore that particular step. All right. Now the next step, okay. Now the next step is to bring in the optimization that I just said. So for that, we'll just take the value of character into a new variable just to reuse it. And now this is the question that this is the optimization, the major step in this problem. We just check if the character is not in our trie. So if it is not in the node that we are trying to search in, this node represents the trie. So if it's not in the trie's children, then we can return it. Just so we understand it better, we'll just go and take this element, and we know that at this particular, whenever we get the node element, we just ask if in the next or in the children's of this particular iterator or this particular node value, if it does not have the value of does not contain the value of r or a t or the children values, it's pointless to go in those direction and search for a path. So we'll just return it. So this is the new optimization. By doing so, we save a lot of space and time. Not space, but more of a time. And now let's just go and get the next node value. And why do we need that? We need that to check if that the next element is actually the end of the word. So in order to do that, I'll get the next word, and I'll check if the next node word attribute, if that is equal to, or I don't have to even check because all other nodes will have a null value. All other will have a none value, and only the terminal nodes will have the character in itself. So I just have to say if that exists. That's it. If that exists, then append to my result the value of the next node dot the word, and make sure we don't do it again. So I'll just make sure that I put next node dot word back to none value. Now time to define the actual DFS process. First, the moment we enter a node, we mark that node as visited. So in this case, you can have a visited set. In this case, I'm going to go with the conventional method of marking it as visited. And then I have to go on my right side, left side, down and up. So in order to go down, I say r+1, next row in the same column, but make sure we send the next node element. So if you're right here, we make sure while we call the next function, while the DFS calls the next function, even in the trie, we have to promote this particular iterator to the next step. So in order to do that, we just say while we do the DFS function, we supply the children or the child of the current node. So after doing that, I'm just going to copy and paste it 3 more times. Yeah, and replace the values accordingly. So r-1 will go up, the same row and column +1 goes down, column -1 goes up. All right, after I do all this, it's time to replace the board value, unmark it as visited. So I'll go to board, r, c, and replace it with the character element that I saved it right at the start from the actual value. Now I just have to finally return the result value. Yeah. So okay, in the DFS function, I'm not returning the result value. That result is something that we get in the final step. So I just have to return. I have to stop the execution. You can just remove the return as well. Python does it anyway. Now we are entered the driver function, actual driver function, where we go traverse the entire board that is given to us. In order, since this is 2-dimensional, I'm going to do a 2 for loop. So 2 for I in the range of the len of the board, and for j in the range of len of the board of 0, I'll do a DFS, supply the row value, the column value, and our root value as the initial first node that we have, the initialized root node first. Now finally, we will, if the next node dot word, if it hits upon this particular if condition, we know that all our results will be stored in result. So we'll make sure after we traverse everything, just return the result. That's it. If we do this, we'll be able to optimize it and get a solution. Let me just submit this solution, and what is wrong in the constructor? It should be underscore underscore init function underscore underscore followed by a self value and the end of it. Oh, typos here. Children. Alright. Now that we got rid of our errors, let's just try and submit it. And we see for this given problem, it will pass the time complexity as well. Alright, with this we'll conclude this video. Thank you for watching.